Hello everyone. Today is day 11 of our challenge doing 30 deep learning projects in 30 days. We will be solving this challenge called Apply Transfer Learning with VGG16 for a simple classification task. So it is going to be a classification task where we might have to classify between cats and dogs. This is something new that we are learning. That we are doing. Ah, so yeah, let's get started. Before I start, the flow is going to be same. I should mention that the flow is going to be same. That we will be using the same context window as we have used for solving our previous problems. I will go and ask this to help me out with solving this problem from ChatGPT. And yeah, whatever new I learn, whatever anything I see that I don't understand, I'm going to ask. The intent of doing this challenge is to learn gradually by doing. So yeah, let's start. Say I'll say, hey, it is day 11, and here is the problem statement. So it is generating. Uh, okay. It says let's wait for it to generate the response completely, and then we are going to understand. So it says that it is a fantastic challenge for day 11, where transfer learning is one of the most powerful techniques in deep learning, especially for computer vision tasks. With transfer learning, you leverage a pre-trained model like VGG16 that has already learned features on large datasets such as ImageNet, okay, and apply it to your own problem. So it says it is a complex, it is, I'm so sorry. So it says that it is a powerful technique in deep learning and in computer vision. We are going to leverage a pre-trained model called VGG16. So it is a pre-trained model, and apply a ImageNet type of data set. No, that has already been trained on this large data set. So we are going to apply it on our own problem. So what is transfer learning? Transfer learning involves taking pre-trained model which has already been trained on large dataset and fine-tune it to perform a new task. Oh, this is interesting. I might use this technique in future bigger problems. Good. So transfer learning involves that we have pre-trained model like VGG16. So in transfer learning we use the pre-trained model, they which are already trained on a large data set. We fine tune them to perform our new task. Okay, this is useful when you have limited data, or when or want to make use of knowledge captured by a powerful model. Okay, VGG16 is a well-known pre-trained model from ImageNet that consists of 16 layers and is very effective at extracting useful features from images. Okay, so it is now talking about VGG16, which is a powerful pre-trained model trained on ImageNet uh, dataset that consists of 16 layers and is very effective at extracting useful features from the images. We are going to use it, a powerful pre-trained model. So I do understand. I don't think I have to go and ask again, explain transfer learning with example. I understand that in transfer learning we are basically using the pre-trained model that are trained on a large data set. We can fine tune it based on our demands to perform our task. So we will be using VGG16 model pre-trained on ImageNet and applied to a new classification problem. Okay, and then we can either choose a simple data set like cat versus dogs, or use a small subset of CIFAR 10. Okay, we will freeze the convolutional base of VGG16 to use it as a feature extractor. We will freeze. We will freeze the convolutional base of OK, and use it as a feature extractor, and then add custom fully connected layers on the top of our. Okay, this is how we are going to make use of the VGG16 by freezing the base convolutional layer to extract the important features, and on the top of it we will apply our own convolution or own connected layers. So let's start. Let clear this terminal, close this 10-day problem, date and problem, create a new file for day11.py. Not this. Let's okay. I have not added it to my Git repository. I'll add it later, but let me mention what the problem is about. So I'll go copy the problem. Then I'm going to do what? Okay, sorry. Let's import the libraries first. So we are going to import how many libraries? First, we are going to import application from garage.application VGG16, garage.model sequential, garage.layers. How many layers we want? Dense, flatten, dropout, and then we want image data generator that we have learned about on day 10. How to augment, how to do data augmentation on training data using image generator, and then we will import pyplot to plot the performance, to visualize the performance. So let's do that. TensorFlow application, not import from this. Import VGG16 from TensorFlow models. Import which model? Sequential model from TensorFlow layer. Import dense layer, flatten layer, dropout layer. Yes, from TensorFlow keras to layers, not layers. In preprocessing image, import image data generator, and then at last import matplot pyplot as plt. Now let's do what we are done with it. We have imported everything. We will load the VGG16 without the top layer. Okay, and we will add our own top layer. So let's do that. Step number 2, not mentioned. Step 2 will do load VGG16 without the top layer. We will do what? VGG base and load from VGG16. What do we mention? The weights are, let's understand it first. Here we mentioned the weights are, so what, which, here we mention it is going to be pre-trained on ImageNet dataset, so we mentioned that. And then we mention this input top false. This means that we are excluding the fully connected layer at the top of the network. We only want the convolution layer. if you remember, when we did our first problem on CNN, which was on day 8, we learned that how many layers the CNN model has, and we learned that it has a top fully connected layer, so we will be excluding that layer, and we exclude that layer by using this argument called include underscore top equals to false. Okay, by doing this we are excluding the fully connected layer. Then we need to mention the input shape. The This is because in the first layer we mention the input shape, and then in the following layers we don't. This is the shape of the input images. They are the We resize the input images into 150 into by 150 pixel with three colors RGB channels. Okay, let's do that. Weights is image net. Then include top. I'll say false. Don't include top. We will add it later. Input shape is going to be 150, 150, not multiply, 150 of three channels, red, green, blue, and this is it. Now we will go and do what? We do this VGG based or trainables, we set it to false because we want to freeze the convolution base so that it is not trained again. So what are we doing? We are freezing this layer, which we will use to extract the features, and so that this layer will not be trained again, during the training. Let's do that. VGG based dot trainable. I'll say no, freeze the layer, freeze the base layer base layer, so that it is not trainable again when will be doing training. We'll look at the summary. VGG base summary. We'll look at the summary. Now let's add our custom layers to the VGG16 base. Add, not remove extra space, add custom. Let's do this, and yeah, let's add custom layer to VGG16 base layer. Okay, uh, we'll do what? We'll add a model, sequential model. Let's understand the code first. Here we add the in base layers using the model dot add, and add the base layers. Then we apply flattening because we want to extract whatever features it has extracted. We want to flatten it into a single list, one dimension list. And then we add our own fully connected layer with the activation function rectified linear unit, and we will have 256 neurons. Why? Because each neuron, RGB color, they are usually depicted between 0 to 255 of range, so that is why we have 256 neurons. uh, and then we add the dropout layer because we want to prevent the overfitting. And then we want to apply the classification, so that is why we have two neurons. Now since we want to apply classification, how do we apply classification? Based on what probability value each neurons holds. Whichever will hold the maximum will be the final output. Now if you want to output the probability, so we use the activation function as softmax, and then we apply the compile the model using using the option that we have been using for the uh, basic classification type problem. and then we print the summary. So let's do that. Add the base layer, model dot add VGG base, then we add our own layer. How do we add? First we flatten it, the extracted features into 1D, then we add the not what fully connected layer. How do we add it? It is going to be a dense layer of 256 neurons, and the activation function is rectified linear unit. Then we will add the dropout to control the overfitting. The dropout will be of 50% drop. Then we will add the output layer, which is a dense layer and will output two neurons, and each neuron will be a probability for those two classes, and whichever will be having the maximum probability will be the final result. Now for such cases, the activation function is softmax because it outputs in the form of probability, and the sum of the probability of all the neurons it is applied on is 1. And then we will do what? Compile the model. Once done, we will compile the model. So we'll do what? Model dot compile. Here we mention the optimizer as Adam, the classic one that we have been using. Then what do we mention? The loss function. How do we calculate the loss? We calculate the loss using sparse categorical cross entropy. Why this one? Because we have binary classification, which is in the form of numbers, so sparse. Now again it is a classification, so categorical, and then cross entropy. Now we want to do what? What do we want to measure? We want to measure have the maximum accuracy, so we'll say accuracy, and then we will print the summary of this model. Once done, we will set up the data augmentation using image generator. If you remember, yesterday we did that, right? Yesterday we added that. And why do we add it? First we add it because it helps in expanding the training data on multiple features. It covers many variants of the training data by applying these techniques like rescaling, rotation, zooming, horizontal flip. By applying these techniques, it creates more variation in the training data. And why do we do it? Now we know how it is done, but why it is done? So we do it because we want to prevent overfitting. And what is overfitting? Overfitting is that the model is performing good on the training data but is not able to perform good on the validation data, the unseen data. Now if we provide model the as much variance as possible, the model is going to perform good. Okay, the model is going to see the many variations in the training itself only. So eventually it is going to perform good in the unseen data, on the unseen data, right? So that is how it is helpful. So we create the data generation settings, and then we create apply on it. So we'll create this, the train data generation. We only rescale the validation images. Okay, we are going to rescale the validation images only. Image data generator, so we can rescale using the image data generator. Okay, nice. And then it says that the validation images are only rescaled without augmentation to evaluate model's performance. Okay. And then we load the data using flow from directory. You need a directory of images. Okay. Directory with training images. Resize all images into this, and class model is going to be this. And then we need to have a directory with validation images. Okay, and then it is going to generate the training images and the validation images from the flow from directory with these settings. Okay, and then we are going to train the model and visualize. I Let me go here. Okay, and if I want to look at the data, okay, I have all the images, download all. How do I accept it? Let's go back to this thing. It, let's accept the competition terms and conditions. We are not performing the competition. Let's download everything. Let's save it. Save it. Now let's go here. It says that the permission was denied. Let me try it again. Let me ask the ChatGPT only. I'll say I don't have images for training and validation that has been asked to put in the directories in which function? Let me go back to this flow from directory. Where can I get the images from? Let's wait for ChatGPT only to answer me, right? I'm using it to understand this concept. Okay, search for datasets like cat versus dogs, flowers, or any other interesting. Download the dataset into a local system. So we have multiple options. The option one is use a predefined dataset like cats versus dogs from Keras. Okay, if the Keras provides the dataset automatically, why do I need to download it? So let's do what? Let's download it. Click automatically into the cats and dogs filter directory. Filter directly in the dataset folder where it is going to have two folders, train and validation, cat stock. Okay, then again we have a CIFAR 10 dataset which is available in the KRS, but it is going to have 10 classes. We have explored this dataset many times. uh, what I want to do, I want to experiment, I want to do this one, I want to go ahead with this one. So what I'm going to do, I will do this, and do what, comment everything here. Are we passing anything? No, we have configured only, right? Let's download the data. Download, not download, no, don't mention it here. What we can do, we can mention it here. Download the data set. Okay, and set data set slash, okay, let's do this. How do I place it in the dataset folder of my project? Let's wait for it to generate the response. So it says you it will move it. Is it set into the path that is derived from the zip directory? Okay, it will be stored here. Then we will need to move the folder called to the dataset directory inside your project. Okay, this get file function downloads the file to a temporary directory, which is this directory, and then we will move this from set into a path that is derived from zip directory. Let's say it is stored in the subdirectory called the user folder. Okay, let's run it. It will be here. Yeah, we might have to. Okay, let's run it. I'll say python day11.py. Let's wait for it to, and we have the error at, yeah, let's import the TensorFlow. Import TensorFlow as df, and now it should work. Downloading. So it is downloading from this location. Okay, it has downloaded the data, and I want to see everything. I can also go here and download. It has downloaded actually. Wow, I, I would have done this. Why am doing? So if I go here, unzip it, and now I have data here. So I'll move this from my this move. So instead of doing that, I can download the mention it that we can download from data set will be this one. Okay, and yes, we need to download it and place it here. So what I'm going to do, I have already downloaded it, so I'm going to place it from the cat dogs filtered to our dataset folder. Now our dataset folder should have all the cats and dogs in images. Wow, it has how many images it has? It has it has 1,000 images. I also have two cats. I could have used those two images. Wow, cute, no? Yeah, I can. Yes, and then dog also it has I guess the same images, and here it has okay it has lesser images in for validation, but yes, let's remove them. Dog, yes, so we have the data set now. Let me close it and place into the dataset folder. Let me open the uh, script for today, and yes, I'll say load the I'll say download the data set and place it in the dataset folder of your project. Okay, we are done with the dataset. Now simply we'll go to our steps, the original steps. So the step was to set up the augmentation. So let's come here. It is set up data augmentation for training images. Set up data augmentation for training images. Okay, so I'll say train data generation immediate data generation. We pass the rescale will be normalize the pixel value from 0 to 1. Okay, the pixels are in the range of 150 into 150. I mean, are in the range of 0 to 255. So we need to rescale it. How do we rescale it? We rescale it between 1 to 250, 1 to 0. Sorry, 0 to 1. So we do that, and then we rotate the image by 15 degree. Rotate range will be 15 degree. Then we apply width shift by 10%, height shift by 10%, zoom range by 10%, and horizontal flip. Yes, we want that. Let's apply that. 10 height, not height, shift 0.10, width height, zoom range 0.10, and horizontal flip. Yes, we want that. We have created the setup the data the object for data augmentation. Now now we also rescale the validation image. Only rescale rescale the validation image. How validation data generation image. Here we mention the rescale 1 point divided by 255 to normalize it between 0 and 1. And we do not apply anything like this on our validation data. We only want to add these variations on our training data. We just want to rescale our validation data, right? So let's do, let's not fit, we will use flow from directory to apply this data documentation. Let's part to the directory is going to be data set cats and dogs. What is the full name? Cats and dogs filtered. Okay. And then we have, no, we have one more thing, right? Train, train data. Then we want to mention the target size. Resize all the images to 150 by 750. Target size. Target size is resize all the images to 150 by 150, whatever the images size are, whatever the, yeah. Then in what we need to mention the batch size, it is going to process in 32 images. And then we want to, what is the class mode of categorical labels? The class mode of categorical labels is categorical. What does this mean? Let's understand what it is. In the flow from directory to specify how the labels of the class should be generated and represented during the training. Let's break it down in simple terms. This means, it means that the labels are represented as one hot encoding vectors. It is used for multiple class classification tasks where each image can belong to one of the many class possibles. Okay, so class most categorical means that it is going to have multiple classes 0, 1, 1, many. Let's say it can have cats, dogs, and birds. I don't think we should go ahead with that because we have only two types of images, cats and dogs. So we will go ahead with class mode binary, where we have only two possibilities of the classes, cats and dogs. We do not have multiple. If the class mode is sparse, we have uh, similar to categorical, but instead of so similar to categorical, here the classes can have multiple classes, but here the labels can be in the form of integers 0, 1, 2, 3, 4, 5, 6, 7, 8. Yes, and then we have two more which we do not delve into right now because you know what, why to read more and consume my brain in something that I'm not using right now, right? So yeah, we need to mention the class mode that the labels are in the form of. We are, ChatGPT says to use the, let's go back to the code. ChatGPT says to use the categorical, but I think we should go ahead with using binary because we have only two type of classes, cats and dogs. So I'll say class mode is classes, not class mode is going to be binary. Then we will apply on flow from directory from on our training data. So the directory is going to, I'll copy it. Oh, I'll mention this. This is the better filter train. Yes. Now here we mention it is validation. And what else we want to mention? Again, the target size of the images will be 150 by 150. The batch size should be same. Let's keep it same. The class mode is again going to be binary. Yeah, done. Now let's train the model. Train the model dot fit. We will train the model. Before that, let's save everything into this variable history, all the training information. Let's pass on the augmented data, augmented training data. And yeah, okay, store it. Train generator, it is, and validation data generator, train generator, validation generator. So we are going to use this train generator, the object here, which is going to call this one. And steps for epochs. S- steps steps per epochs. How many steps per epochs we will have? This is number of the batches to run per epochs. It is calculated by dividing the total number of samples by the batch size. Okay, how many steps per epochs we are going to have? We will have train generator dot batch size that we have mentioned here. How many epochs you want? So before first that validation data is going to be validation generator, and the validation steps is going to be validation generator dot samples. Did we mention samples anywhere? No, we did not. Yeah. um yeah, this will return the batch size for the generator, validation generator. Then how many epochs you want to run? We want to run 10 iterations. And do we want to see everything on the terminal training information? Yes. Now once done, we will visualize the performance. First we'll plot the loss. How do we do that? We need to first, before that, create a data frame of our history variable. So we'll do that using pandas. First import the panda library, import pandas as pd, and we create data frame out of history. Once done, plot the graph to define the figure size. It's going to be 10:6. Yes. Then plot the loss first. The label is going to be training loss, and we have the same typo. Then we will plot the validation loss. Label is going to be validation loss. Then we will, what would be the x-axis represents epochs, and y-axis is for the loss and should be in the form of string. And then we should the title is, we are looking at the training and validation loss, and we want to see which line represents what. We'll do that by using this legend function, and then we will show the plot. Now we will plot the accuracy. So wherever you see accuracy, just loss, replace it with accuracy. Here also capital accuracy. I'll capitalize it. And do I need to do anything else? No, we are done with it. So I'll now remove those extra lines. I'll again maximize the terminal, and let's do what? Let's run the script day 11 and wait for it to train our model and see information of each epoch. The estimated time for our epoch is going to be 30 seconds. We have 10 epochs. So what does that mean? Huh. 300 seconds. So we have 300 seconds. So what you should do? 300 seconds into, why I'm so weak in the maths? I'm not weak. I guess I've used all my brain. Wait for 5 minutes for it to completely drain, or you can fast forward it to the next 5 minutes. And then I will be looking at the full validation and every data so that we can study the performance of the model. Um, so yes, you can easily fast forward it to next 5 minutes. I'll wait though. I'll wait for it to completely train. Your input ran out of data, interrupting training. Make sure. Okay. So our data was not sufficient, I guess. Okay, we are almost there. We are on the uh, ninth epoch. Another 30 seconds and we are done. Okay, we have error. All arrays must be of the same length. What is 84? What do we have on 84? We cannot visualize it. Very bad. Okay, I would have received. Okay, I use the first. Okay, I ran the model and script, and here is what I get on first epoch. Also, the rest of the epoch ran fine, but this failed with this error. And instead of if you would not have to ask ChatGPT, I can simply go and look into this. What is there? I mean, how many columns it has. Maybe this should be changed to batch size. Hmm. Okay, so we have two problems. First problem is your input ran out of the data, interrupting training. This error typically occurs because the number of steps specified during training is more than the number of batches the data generation can provide. Here's the detailed explanation. Yeah, I understood that. How do we fix it? So the error is says your input ran out of data, usually which means steps per epoch's value you provided is greater than what the dataset can actually provide. So dataset is smaller, yes. Steps per epoch tells the model how many batches it needs to process in each epoch, right? If steps per epoch is too high, the data generator may run out of the data before reaching the number of, yes, it is too high, but we do not have that much data. So how do we evaluate correctly? We do that using the dot samples instead of batch size. The dot samples means the total number of training samples. The batch size used for during the training. Okay. So we can avoid by this samples. Okay. So instead of batch size, we are mentioning samples. Correct. This way it will resolve the first problem. Then it says that the second error indicates that there is an issue with training history, that history data when trying to convert it into a partner data frame. This usually happens when the length of arrays of different metrics like loss, accuracy, validation. Okay, we might not have it because yeah, it got stuck, right? So we can simply do history and then figure it out. Let's run it again. Maybe this will fixing the first will solve the second issue as well. So let's run it again. Now I will simply fast forward it for you, but I'll keep looking at it. So yes. we still see the error. So I think we are going to get the, we still see the problem. We still see the problem. Samples. How many epochs, steps per epochs we have? 32. 32 into 10, 320, but we have 10, 200 only. 3. Okay, and our, it performed nicely, but we have now getting this, and this is the, yeah. Let's see what ChatGPT will say for this. Yes, steps per epoch and validation steps configuration model fit. Okay, we train the model with correct. Okay, okay. If I do this, if I do by train generator dot batch size, and this is also validation generator batch size. Let's run it, and then we will understand later. It is going to take 1 minute, so yeah, I will fast forward this as well. So it has, I guess, almost ran our first epoch nicely. So we do not see any problem with the first epoch. But yes, let's wait. So the samples means the total number of training images we have. Yeah, it ran completely with this information. It has 20,000 images for training and 10,000 images for uh, yeah, for validation, I guess. Now, how the steps per epoch will be generated? This will be the total number of training images, and let's say 2000 divided by the batch size is 32. So we'll have 2000 2000 divided by 32 will be 62.5. So 62 will be the batch size, steps per epoch. So that is that way it is not going to cross it. Okay, nice. Oh, I was checking out my bookmarks. Okay. Okay. Okay, so the training is done. If we look at our training, we see that the loss was started with 0.69 and ended with 0.23. So there is good uh, performance we see here. And then the accuracy was at 85% initially and then closed at 90%. The validation accuracy started with 83% and closed at 88%. This is also good. Then for validation loss started with 0.34. It should end at 0.37. This is also good. Now overall the performance of the model is good. Now let's look at the plot of loss across each epoch. We see that there is huge drastic, like sudden decrease in the loss, which is really good sign, and then gradually it is decreasing. For the validation also it is gradually decreasing, and what at one point on the epoch 6 it increased a little and then decreasing. So there are not many bumps in the uh, validation loss, so it is a good sign. So let me take a screenshot of the thing. And if we see the accuracy, again it is a good sign that the accuracy for the training data, there is a sharp increase and then it is gradually increasing. And for validation there are, it is increasing, decreasing, increasing, then going stagnant, increasing, and then going to the previous value too. So this is also good, not that bad. So yes, we have successfully trained the data on our classification type of model, sorry, data set. What was more important here today is that how we have done what how we have used the pre-built model as the base layer. So if we go to the summary of our model, the VGG16, this is the model how it looks like. Input layer has 150, 153. See, that's what we have mentioned here. The weights are image net, and do should it include the top, the final output layer, the fully connected layer? No, it should not. We are going to add that with our custom model, and we see that how many convolution layer it has added. See, so we do not need to do that. We have simply used it as our base model. Now, if we look at our custom model, we see that it has added the VG6661, a functional type layer, as the base model to our custom model, and then we have the flattened layer to converted into a single 1D array, then dense layer, dropout layer, and the final output layer. So now our model looks very simple and sweet, but the base layer is already complex and already been trained on the large data set. So this is really good that we see here. We do not have to reinvent the wheel. We just have used the pre-built model. So this is something cool that we have learned today. So now I'm going to do what? Going to uh, add the day 11 code, and commit, I mean add it and then commit it with that add code for day 11, and then push it to our main branch. Let's see if we can see the data. Yes, we can see the code here. See, the code here is, yeah. So yes, today was a fruitful day, but it was a long training day, because the model took training, in model took a lot of time in training. So I'll simply go and close this video for now. We'll come back tomorrow and solve the day 12 problem. Thank you very much.